This is a quick video on the gameplay of our game. So now we're going to get into the good and nice science behind all of this. So Newton's first law of motion. Newton's first law of motion states that every object at rest stays at rest, and any object in motion will stay in motion unless acted upon by an unbalanced external force. And to model this, in our carnival game, we have a web shooter. When the web string is at rest, it will stay at rest until an unbalanced force reacts with it, and that unbalanced force, it can be observed with the compression of the spring and the piece that blocks the spring from shooting the projectile outwards. When that projectile is brought down, it moves. And likewise, when the projectile is in motion, it wants to stay in motion, but it hits an obstacle which causes it to stop. Next, we will be looking at Newton's second law of motion. And this it has a lot of math into it. And this says that a force required to move an object is directly proportional to the mass and acceleration of that object. You've probably learned about the famous formula F equals ma. This stands for force equals mass times acceleration. The mass of the web string or projectile and the force applied to the spring will cause the string to accelerate. And this acceleration is also proportional to the force, the kinetic energy, and also the mass of the projectile. And there are also external forces that also affect the acceleration. First of all, we also have air resistance. Air resistance is a really important thing that we can also see in planes or cars, or even in F1 cars. Air resistance is a really important thing that F1 cars specialize in. When the web string slams into the Spider-Man villain, it will slow down and change direction. This is also an example of friction as well. When it slides down on a friction-like surface, like on the conveyor belt, this will also cause it to slow down, and likewise the air resistance. And these are also ways, just some fun facts about the acceleration effect. Next, we have Newton's third law of motion, and this one is a really important one. It states for every action there is an equal and opposite reaction. In a few couple of seconds, I can summarize this as forces come in pairs. What this means is if you're standing on the ground, you're exerting a force on the ground, while gravity is also exerting a force on you to push you back up. You can observe Newton's third law of motion when you shoot a projectile from the web shooter. What happens is the projectile wants to keep moving due to Newton's first law and it stays at rest, but due to the unbalanced force of the spring, it moves forward. Now, since humans are extremely heavy relative to the projectile, we don't see any sort of reaction to that. But if we were really, really small or a massless object, we would move backwards due to the reaction. Likewise, when the projectile hits a target or misses a target, it will still hit something, and that thing will also exert an opposite and equal reaction. And this is how they all apply. This is how everything combines together. We see the first law of motion when we shoot the projectile. We see the second law of motion when the projectile is in motion. We see the acceleration, the force, the mass. We see all of that. And we see finally the third law of motion as the projectile hits a target. It's convenient that the steps we can observe the laws are in first, second, and third in the chronological order. Next, we have two types of energies. The first one is potential energy, and then the next one will also be kinetic energy. These two are really, really important, and they are inversely proportional. Inversely proportional is a mathematical term where the greater you have of one thing, the less of the other thing you have. So the more potential energy you have, that means the more less kinetic energy you have. Potential energy is the energy stored inside of an object. It's kind of like inertia. It wants to move, but it simply can't because of the circumstances. That is the potential energy. And for potential energy, we have to use an interesting formula to calculate the potential energy of a compressed string. And that involves taking a lot of spring constants and measuring the compression of the string, but I won't delve into all the mathematical details. But it's really interesting. And potential energy and kinetic energy is measured in joules, and the potential energy is zero point zero 0.01 joules. Next, we have kinetic energy. Kinetic energy is when an object is in motion. Anything is in motion, it's where the potential energy is converted into kinetic energy. Here as well, we use a similar type of formula. You can see we have 1/2 times mass times velocity squared. That is equal to the kinetic energy. And we can calculate the velocity using Newton's second law, and then the mass using any type of scale, and then the simple mathematics, and we get that it is 0.45 joules. And you can also see kinetic energy in a lot of other things. We can also observe the kinetic energy in the conveyor belt. We can also see the potential energy. I didn't mention this, but also in the conveyor belt when it is at rest. Now, I hope you enjoy our game. I hope you play our game. I hope you understand the physics behind the game. And I hope you are interested to learn more about this. And that is it for our project. Thank you so much for delving into our project, taking time to look at this video, and we really appreciate it. Thank you.